Before working on our next example, let me remind you of the following result that we established back in Advanced Calc 1. So recall that the limit of Sn being equal to 0 can be shown to be equivalent to saying that the limit as n goes to infinity of absolute value of Sn being equal to 0, right? The right side implies the left side implies the right side. So now I want to use this fact to prove several things that several examples that I'm going to demonstrate next. So let's look at the example number 2. What I want to do, I want to show that f of x equal to x times sine of 1 over x, that this function is continuous at x equal to 0. Now, clearly, the way I just defined it now, this function is not going to work at 0, so I need to modify it a little bit so that it is. So let me rearrange things a little bit. What I need to do is I need to define the function at 0 itself, which I'm going to do in the following way. So there will be a piecewise definition. It is x times sine of 1 over x if x is not equal to 0, and then at 0 I'm going to define it just as 0. And so now I want to show that this function is going to be continuous at 0. And once again, we have a couple of approaches that we can use. Approach number 1 is to use a sequence definition of continuity. So for that, I will need to take a limit. First of all, before I take a limit, I'm going to choose any sequence xn such that the limit when n approaches infinity of xn is equal to 0. Right, because I'm trying to demonstrate continuity at 0, so continuity at x equal to 0 means that I choose any sequence of xn that goes to 0, and I have to prove that the limit of a sequence f of xn must also be 0. All right, so we need to show like I said, that the limit n goes to infinity of f of xn is equal to f of 0, f of x0, which is, in this case, f of 0. And f of 0 itself, of course, is 0 because that's how I define my function at 0. All right. So what we're going to do, we're going to consider the function or rather the sequence xn sine 1 over xn. Right, that's my sequence of f of xn. And I can see one thing pretty clearly. So because sine of anything, in particular sine of 1 over xn, is always less or equal than 1 in absolute value, we have that xn times absolute value of xn times sine of 1 over xn, that should be the same thing as absolute value of xn times absolute value of the sine of 1 over xn, right? That's suggested by the properties of the absolute value. And this should be then less or equal than absolute value of xn, because sine of 1 over xn is, in absolute value, is less or equal than 1. All right, so if that is the case, then by comparison, theorem, one other thing that I know actually is that absolute value of xn, oops, sorry, absolute value of xn is, absolute value of anything actually, is always greater or equal than 0. So by comparison or squeeze theorem, then the limit of 0 is 0 as n goes to infinity, right? Limit of xn as n goes to infinity is also 0, because that's how I chose my sequence xn. And so limit of xn is 0 by this result that I recalled in the beginning, saying that the limit of a sequence is 0 is the same thing as saying that the limit of absolute value of the sequence, of the elements of the sequence, goes to 0. So that means that absolute value of xn goes to 0, and then the term of my sequence is going to be squeezed between zeros. So the limit as n goes to infinity of absolute value of xn sine 1 over xn, this is 0. But then again, by the result that I asked you to recall, saying that the limit of something, of absolute value of something is 0, means that the limit of that sequence, the absolute value of which you took, is also going to be 0. So therefore, limit n goes to infinity xn sine 1 over xn, this is 0. And which is basically the same thing as saying that the limit n goes to infinity of f of xn is f of 0, and so we're done, right? Because then the definition, sequential definition of continuity is satisfied. Let's try approach number 2. And here we're going to verify epsilon delta definition. So I'm going to choose any epsilon greater than 0. And what do I need to show? I need to show that so what is my epsilon delta definition? For every epsilon, there exists a delta such that something happens, right? So I need to show that there is a delta greater than 0 such that In this case, I'm looking at the continuity at the point 0, so such that x minus 0 being less than delta would imply that f of x minus f of 0 is less than epsilon. So how do we choose delta? Let's suppose for a moment, right, so that epsilon is greater than absolute value of f of x minus f of 0. What would this mean? It would mean that x sine of 1 over x, that's value of f of x, 0 is a value of f of 0, that is less than epsilon. But of course, because I am subtracting 0, right, this is the same thing as absolute value of x times sine 1 over x. And of course, again, absolute value has a property that absolute value of the product is a product of absolute values. X times absolute value of sine of 1 over x. Okay, so I want to make this less than epsilon. So how about this? Forget about this being less than epsilon yet. And let's use the fact again that sine of 1 over x, as any sine of anything, the absolute value of that is less or equal than 1, so this should be less or equal than x. And then what do I want? I want that to be less than epsilon. So the conclusion that I can draw from this computation, right, it's the same thing as we were doing before. It looks the same as we were doing before when we were proving that the limit of a sequence exists and equal to something. What I have shown is that if absolute value of x, which actually is absolute value of x minus 0, if this is less than epsilon, then absolute value of x times sine 1 over x minus 0, that is also less than epsilon. So then clearly, if I choose delta to be equal to epsilon, I'm done, right? Because I pick epsilon. If I make x minus 0 less than epsilon, then f of x minus f of 0 is less than epsilon. So just take delta equal to epsilon. Okay. Let's try another example. Example number 2. So that would be actually example number 3. I want to determine whether f of x defines as follows: sine 1 over x is not equal to 0, and 0 if x is equal to 0, if this guy is continuous. Is continuous at 0, x equal to 0 still. So in this case, what do we expect? Do we expect that this function is going to be continuous or not? Just to motivate what will follow, let's sketch the graph of this function. Oops. In fact, this is not just sine of 1 over x, this is f of x. All right, so value at 0 is equal 0. That's easy. Then if I look at sine of 1 over x, well, what would I see? So first of all, I know that sine is always between -1 and 1. So if this is 1, and this is -1, then my graph is always going to lie between these two values. Actually, it doesn't look too good. Let me try to redraw this. Okay, slightly better. Now, if I look at a value of 1 over x, when x goes to infinity, 1 over x goes to 0, so sine of 1 over x goes to sine of 0, so which is 0. So that means that at infinity, this function will have a horizontal asymptote of 0. And at minus infinity, it will have a horizontal asymptote 0 as well, because limit of 1 over x when x goes to minus infinity is still 0. X goes to minus infinity, 1 over x is negative. So the function should approach 0 from a negative side, because sine of a small negative number is negative. And likewise, when x is large positive, 1 over x is small positive, so sine of a small positive is a small positive number. So that means that the function will go to 0 on this end and to 0 on this end, but from opposite sides. Now, what happens to 1 over x as x approaches 0 from a positive side? Then 1 over x is going to go to infinity, to positive infinity. And what happens to the sign of the argument that goes to infinity? It oscillates infinitely many times. So as we approach 0 from the right, sine is going to oscillate infinitely many times. So it means that the oscillations are going to become faster and faster. So very roughly speaking, first you see fairly infrequent oscillations, but then they become more and more frequent. And the same thing should happen from the other side. Of course, my graph stinks, but I hope you get the idea, right? In fact, this function should be odd, right? Because 1 over x is an odd function, and sine itself is an odd function. So what does it mean? That if the function oscillates infinitely many times as x approaches 0, that means that that function should have no limit when x goes to 0. And if there is no limit of sine of 1 over xn, then there is no continuity. So I'm going to prove that the function is discontinuous at 0 by showing a counterexample. And a counterexample actually is simple. If I take a sequence of xn such that xn goes to 0 from the positive direction, and let's say values f of xn are designed in such a way so that values of f of xn will always pick the maxima of sine on each period, right? So maximum of sine is always equal to 1. So how am I going to choose my points? Well, so I would want to design xn, I'm going to choose 1 over xn to be such that where is sine equal to 1 at pi over 2 plus 2 pi n. And n is any natural number. So then if I solve for xn, it's 1 over pi over 2 plus 2 pi n. Well, n is in the denominator, so clearly this goes to 0 as n goes to infinity. Also, what about f of xn? So the way I designed xn, right, of course, sine of 1 over xn should be the sine of this quantity, sine of pi over 2 plus 2 pi n. That, of course, is equal to 1, again, because that is how I designed my function. Okay, so if all this is the case, then what do I know? So, hence, limit of xn as n goes to infinity is equal to 0. All right, and if the function were continuous, so if f is continuous at x equal to 0, then limit n goes to infinity of f of xn should be f of 0, and that is 0, right? However, a limit n goes to infinity of f of xn, right? What are f of xn's? They're all 1s, is equal to the limit n goes to infinity of 1, and that is equal to 1. And so therefore, f is not continuous at x equals 0. Okay, so I hope that you got the hang of how this continuity is proved. And so next time we're going to start talking about properties of continuous functions.